Hi, welcome to video 9.10a, Taylor series for special functions. Okay, so a quick review of Taylor and Maclaurin series. Of course, for Maclaurin series, which is a Taylor series near zero, the coefficients are the nth derivative of f at 0 over n factorial x to the n, whereas for a straight-on Taylor, it's the nth derivative at a over n factorial times x minus a to the n. So sine x. Now, so we're going to add to our repertoire now of ones that you should have memorized. So if you forget, you can always go back to the table version for any of these, but you don't want to have to do that every time. So if we take sine x near 0, of course the 0th derivative is the function itself. First derivative is cosine x, next derivative is negative sine x, negative cos x. Then it's a repetitive pattern because the derivative of negative cosine x is sine x, and then they'll start to repeat. Now we're doing this at 0, so sine of 0 is 0, cosine of 0 is 1, negative sine 0 is 0, negative cosine 0 is negative 1, and then of course they repeat, 0, 1, 0, negative 1. So if we write out the terms, of course the coefficients are 0 factorial x to the 0, the next one is 1 over 1 factorial x to the 1, 0 over 2 factorial x squared, etc. Well, every term with an even exponent has a coefficient of 0. So it turns out that sine of x near 0 is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. If you remember, that's the one I started out the whole of chapter 9 with. Now, ways to remember. You'll notice that these are all odd exponents and odd factorials. Well, y equals sine of x, if you graph it, is an odd function. It's symmetric with respect to the origin. So that's a way of remembering that it's the odds. So in summation notation, obviously it's alternating. It's negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, 2n plus 1 being odd. And if we start at 0, everything works beautiful. That means the first term is x to the 1 over 1 factorial, negative 1 to the 0, right? And is 0 will be positive. Okay, now to get cosine, if you've memorized what sine is, it's pretty easy to get cosine because it's the derivative of sine. So if I take the derivative of x, I get 1. If I take the derivative of x cubed over 3 factorial, I'll get 3 times x squared over 3 factorial, which is x squared over 2 factorial, etc. You can look at it summation-wise. If you take your negative 1 to the n as a constant, and then I am differentiating, oh, it's over here. So I have negative 1 to the n over 2n plus 1 factorial, because this whole thing is all n's. Then I'm differentiating x to the 2n plus 1, which will be 2n plus 1 times x to the 2n plus 1 minus 1. Then what happens is the 2n plus 1s, this is 2n plus 1 and this is 2n plus 1 factorial, which is 2n plus 1 times 2n factorial. The 2n plus 1s cancel, and sure enough I'm left with x to the 2n over 2n factorial with a negative 1 to the n, also starting at 0. So what happens here is this ends up being 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. So again, it's an alternating series. This time all the exponents and all the factorials are even. And of course, if you draw y equals cosine of x, you'll notice it is an even function. It's symmetric with respect to the y-axis. So you will want to have both of these memorized. Sine is odds, cosine is evens. It does start at x to the even 0 over 0 factorial. So and this starts at x to the 1, which is odd over 1 factorial. Okay, so now that we know the series for cosine of x near 0, this is the cosine of pi x. All you're going to do is just replace x by pi x. That's it. Replace all the x's by pi x. And replace the x over here also by pi x. So if I take x to the 2n, replace the x by pi x, I get pi to the 2n, x to the 2n. The rest stays the same. If you want number 36, 2 sine of x cubed, you'll start with sine of x, you'll replace x by x cubed, and then you'll simply multiply by 2. So it's 2 steps. So here's our sine of x, which was our odd one. We're going to replace x by x cubed. So you go through, replace all the x's by x cubed, including here. And then you multiply everything through by 2. So here's the first few terms, and summation notation is just this times 2. Boom. To get arctan, of course, arctan is the integral of 1 over 1 plus x squared. So we start with 1 over 1 minus x, which is our geometric power series. We replace x by negative x squared to get 1 over 1 plus x squared. So again, replace all the x's by negative x squared. You go through that, replace this x by negative x squared. You'll get negative 1 to the n, x to the 2n. And then we now integrate that. So when you integrate 1 over 1 plus x squared dx, you get tan x. When you integrate by term. Negative 1 to the n is unaffected. It's just a constant. X to the 2n is integrated to become x to the 2n plus 1 all over 2n plus 1. This is a list from the book. You don't really need to memorize 1 over x. I personally would prefer you know 1 over 1 minus x rather than 1 over 1 plus x, but that's fine. ln x, again, it's not a big one that comes up a lot. You could recreate that, and that's near 1, by the way. As you can see, if it's between 0 and 2, the middle of that is 1. And then, of course, is our exponential e to the x. There's our sine x. There's our cos x. And there's our arctan x that we just did. And people often look at sine x and arctan and go, aren't they the same? But don't forget, these are factorials. The denominator, these are not. So these are the ones that I think you should know: 1 over 1 minus x, sine x, cos x, e to the x, and arctan x.